Hydrogen. It's currently the it element, which is a hilarious thing to say, given that it's the most abundant element in the universe, and it's the first item on the periodic table. But the idea of using hydrogen as a clean fuel to displace fossil fuels is certainly very attractive. Aside from the energy that's used to produce the hydrogen, one of the biggest obstacles to its adoption is actually the challenge of both storage and transmission. Now, the biggest problem with hydrogen is, ironically, its very, very small size. As the smallest atom, hydrogen has this unique ability to slip past seals and impregnate seemingly solid materials. In engineering and infrastructure management, most professionals are well aware of the concept and the dangers of hydrogen embrittlement. That's where hydrogen atoms permeate solid metals, mostly steel, and then once absorbed, the hydrogen then lowers the stress required for cracks to initiate and propagate, and it results in embrittlement. Now, there's a lesser known but related phenomenon, which is embrittlement's equally dangerous cousin. That's called hydrogen wear. Hydrogen wear of metals occurs in both sliding and rolling contacts that we find in rotating machinery. So think of common components like bearings, gears, and hydraulics. The high contact pressures cause a higher rate of hydrogen absorption and therefore an abnormally high concentration of hydrogen. Now, how do we know this? As early as the 1960s, scientists like Professor Garkunov in Russia noticed kind of unusual wear patterns in the contact between wheels and rails, and hydrogen wear was touted as an explanation. The phenomenon was actually validated in experiments where they measured the fatigue life of steel balls that were lubricated by a special oil that they'd made up, which was 6% water. Now, what was special about this water? They actually made the water from tritium. So instead of using hydrogen, they used a heavier form of hydrogen, which is also radioactive and therefore gives off a unique signature. When they evaluated the pitting damage after the test, what they found was that the radioactivity in the fatigue zones was 50 times higher than the background that you'd expect just from standard hydrogen penetration. Similarly, they've done other tests where they took lubricant and they impregnated it with deuterium-containing paraffins. So we know that hydrogen can come from the lubricant and it can come from the water in the lubricant as well. So the diffusion of hydrogen into the metal is thanks to a combination of high temperature, high shear, and high pressure that's generated in the load zone. So as the hydrogen then invades the surface, it increases the internal pressure and it causes these cracks to form. Now, repeated cyclic stresses then cause those cracks to grow, and eventually you get the formation of wear particles. Now, why is this important? The mechanism of hydrogen wear was first explained in the 1960s, but research into that phenomenon has kind of stalled, at least in the West. This is really important because unless we have extensive research into the mechanisms, we can't develop modern lubricant formulations that are designed to tackle this particular failure mode. Now that's where Neol comes in. Research into hydrogen wear has actually been continuing in Russian-speaking institutions for the better part of about 60 years. Remember Professor Garkunov that I talked about at the very beginning? There is actually a direct lineage between his research and the development of the CuGlide technology, because Professor Garkunov was the PhD supervisor to Neol's founder and current technology lead. In our next video in this series, we're going to show how the CuGlide technology not only prevents hydrogen wear, but it actually uses the physics of hydrogen wear to its advantage. So it's this perfect example of harnessing Mother Nature's designs to enhance machine reliability.